Okay, so we're doing charges and we're going to look at how forces interact with each other. And here, all the equations link to each other. So we still had the force of two electrons or two charges on each other. And now we're going to have electric field strength. And what is the electric field strength? It's simply the force a charge experiences while it's in an electric field. That's all it is. We know if our field is, if we're very far away from our charge, we are going to experience less of that charge. Just like in magnetism, we can understand the magnetism analogy very well. So we'll stick with the magnetism analogy. Okay, so here we had also done if E is equal to F over Q, we can then use the Coulomb's law equation, stick that in here, and we could get a next equation that will represent our electric field strength, where E is equal to Q over 4 pi r squared epsilon naught. All right, so that's your two equations that we have for E. One is a small equation, one is a large equation. So we have a question. We'll look at the questions afterwards. Let's just go on. Field due to a charged sphere and plane conductor. Now, in this syllabus, they want to know that you know how the electric field varies depending on your conductor and varies depending on your surface. Just like when you had done in CSEC for magnetism, you all should learn, what the magnetic field look like for a bar magnet, what it look like for like poles and unlike poles. Similarly here in unit 2, they're going to ask you to know how several components or several situations differ and what are the mathematical equations that go with them. So again, it's just more of what we did. Well, much more of what we did than CSEC. So reading. Fields will act differently depending on the shape of the conductor. If acting upon a flat conductor, the field passes through one direction. Meaning, I don't need to draw a diagram for that. If I have a plane conductor looking like this, right, my electric field will just propel itself out into space in straight lines. All right, so this is a plane conductor, not plane as an airplane, plane as in flat. Okay. So next thing we know, if a point charge, if you're looking at just a point charge, what this question is, if I have just a point charge, a positive charge sitting out in space, not connected to anything else whatsoever, we want to know how the electric field varies around this point charge. Now, in a point charge, your electric field is going to radiate outwards in a spherical direction. Remember, I told you a sphere is the most perfect shape in the universe. All right. Sorry, I get an email from the school. All right, so your electric field is just going to radiate out in every single direction possible, right? Trillions of directions possible within a field to make up a sphere. So what we're looking at here is a 2D representation of a sphere. It's not a circle, it's a sphere. And what we can do, we can actually find the force or the electrical field that exists within a certain distance of r away from your charge. So that's what we're going to look at today. We're looking at how the field changes due to a point charge. And a point charge, your electrical field is going to radiate outwards. Oh, this is an action note you can put. For a positive charge, it's going to radiate outwards. And for a negative charge, your electrical field is going to be inwards. All right, so if I had a negative charge here, you would have our negative angle. So when you see a question like this, a diagram like this will come from multiple choice, not necessarily your long paper, but it will be here for your multiple choice paper. Okay, so suppose we have a charged sphere. Continue reading, folks. Suppose we have a charged sphere from form 5. We know that charge does not exist within a body, but only radiates on the surface. Whose mic is on? Okay, no longer on. And it only radiates from the surface. Inside a charged sphere, there is zero charge. And this was investigated um, by Tesla and somebody else. I think it was Kirchhoff. But we all know about Tesla. We all know about the brilliance and genius. No, we're not looking at Tesla, the car. Right? We're looking at Tesla, one of the greatest minds ever that you've never heard of. All right. So what we have inside of a sphere, numerous amount of experiments have been done. If we take a sphere and connect it, sorry, more means from school, and connect it to an electrical conductor, whatever, you are going to get no charge inside of that sphere. You're only going to get charge being emanated from the surface going outwards. So within a closed object, you have no charge. That is similar to why if you sit down in a car during an electrical storm and you're not touching any of the metal surfaces, you'll be safe from getting, electrocuted or, shocked to anything. Because inside of a body, you are safe. If you are inside of a house where everything is closed up during an electrical storm, you all are safe because charge does not exist inside of a body. Right? Take your brain and wrap that around. Same thing happens. This is why they put up, this is part of the reading notes you had from before. This is why we have houses that have, not really here in Trinidad because we don't have that sort of big lightning storms and stuff. Right? In houses abroad, especially that have lots of electrical storms, we don't really have that much. Right? They usually have a lightning rod that connects electricity to the ground. Even though you all will be safe inside, that lightning bolt that comes out from the sky can still come down, right? And seriously damage the house. It can damage the house, it can make things catch a fire. But once you're inside a closed body, no charge exists and you'll be safe from outside charge. It's pretty cool when you think about it. Now, it doesn't have to be a closed body, right? When Tesla had tested this, he was inside of a cage. Think like you made a cage out of BRC wire, and he sat down in the middle of that cage and they pumped thousands of volts into it, and he was perfectly fine and safe inside. So, coming out of here, once you know you are inside of an object, you have no charge. Charge does not exist inside of an object. Where it does exist is from the surface. From once you're at the surface, you will have some Q value. And they've actually went and investigated it. All right, and let's look down here. Let's look, we have V being your PD, E being your electric field strength. Now, electric field strength simply just tells us how much energy or how much force a charge is experiences. It does not tell us anything about voltage. We have not looked at voltages yet. Okay, we're looking at something much more fundamental than voltage. Excuse me. So if I have a charge sphere, an electrically charged sphere of radius r, and I took this graph to start from your radius. Let's get a darker marker. All right, your radius here, which is r. If you look here at your graph, we have r. We're going to look at v, and we're going to look at e. In your sphere, your potential difference will be a constant. Why? What is potential difference? It is simply the difference of electrical energy from one point to the other. So your sphere will have charges around it, but not inside of it. So that means once we're inside of the sphere, we have a constant PD because there's no difference in your charge. And once we reach this surface, what this does is matches the surface of your object, your charge, your PD is going to decrease exponentially. Similarly, for your electric field strength, inside of your sphere, you have no electric field strength because there is no charge. Remember, E is equal to F, is it F over Q? All right, yeah, SF over Q. If you have no charge within your sphere, then you will have no electrical field strength. But as soon as you reach the surface of your charged object, you're going to get your maximum electric field strength because electric field disintegrates or diminishes as you move away from an object. Just like any inverse square law. This is again an application of the inverse. Sorry, why did that happen? Okay. This is again another application of the inverse square law, meaning the further away you get from an object or a power supply or any power source, your energy decreases. Same thing is going to happen here. As we move away from our surface, our electric field strength is going to get less and less and less until it cannot be experienced anymore. I don't really want to say it's zero because of the mathematics, you will not get zero, but but there is a point where it can reach to zero. So please know the difference. Let's just clear this up to write it over again. When we have a charged surface, as in we have an object that is charged, here it has a positive charge. Inside of the object, you have no charge. So that means the electric field strength is going to be zero once you're inside of the object. But as soon as you reach to the surface of your object, where all of your charge sits, you're going to reach a maximum value of your electric field strength. And then once you start moving away, meaning you start moving away from your charge, once you start moving away from your charge, obviously your electric field strength is going to diminish because the influence of this charge diminishes the further away you get from the source. So that's how you end up getting an exponential decay curve. Same thing happens with potential difference. Because there is no change in PD in your object, because the energy and the charge remains the same thing. Zero is a number. Remember, it is a number. Okay? It remains flat. It doesn't change your charge whatsoever. Your PD will be zero. And once you reach your surface, it's going to start to diminish because of inverse square law again. So coming on, let's look here. Now, a very special thing happens with charged objects or charged spheres. And let's read from the handout. A strange event occurs outside of the sphere. The field behaves as if it starts from the center of the sphere and not from the surface. We just said that if you have a charged sphere, okay, I don't know what kind of sphere that is, but right? If we have a charged sphere, that the electric field only emanates from the surface. So I would say, so why won't we have like clusters of fields? That makes sense. If it's just coming out from the surface, you can just get clusters of fields coming out. But this is not what happens. We don't get clusters of fields in different points. What it does, it behaves in such a way that it looks like all of your electric fields start from one point in your sphere. So I was really curious. The actual explanation is a whole bunch of quantum mechanics. We're not going to quantum mechanics today. So we just learn to identify how your electric field changes in a sphere or how it exists within a sphere. It looks like all your field lines start from the middle, but of course, since no electric field exists within your charged object, we'll have no lines inside of it. So we're just going to go erase off all of these, and we just have field lines from the surface behaving as if they had started from a centrally located point in the middle of your charge sphere. Potential. Potential at a point, excuse me. Potential at a point in a field is defined as the energy required to move a unit positive charge from infinity to that point. We're looking at potential, not potential differences yet. So what we're looking at here, we're looking at the energy right, required to move. Let's read here. Unit positive charge. That means we're looking at +1 coulomb of charge from infinity to that point. Now, infinity means a very far distance away. Now, a very far distance away doesn't have to mean from here to the moon, which is not that very far. It's 334,000 kilometers. Okay, but when it comes in the realm of charges, remember charges are very, very small. I'll look up to see what is the size of a charge. A distance of 1 meter away from a charge will be infinity because it's so huge compared to the charge itself. So this is where the maths and relativity comes into play. 1 point does not mean the same thing to something else. Okay? I think you all understand what that means. So continue reading. Infinity in this case may be a few hundred meters since a distance of 1 angstrom meter is common when dealing with charges. Remember angstroms? My students who were in the astronomy quiz last year, I pulled you all up with this exact question. You all remember that? Tila?
Yeah.
Jabari?
Yeah, miss, I remember.
Rachel? Right? Angstrom is simply 1 by 10 to the minus 10. It's a special term since we do live in the, not live, since we do have the decimal counting system. Why shouldn't we come up with a special name with 10 to the minus 10? I've never looked to see if there's a 10 to the 10 name though. I can look that up, but in a while. So infinity in this case may be a few hundred meters since a distance of 1 angstrom meter is common when dealing with charges. We're looking at 1 by 10 to the minus 10. Okay. All right. Potential, reading from the handout, potential is a property of a point in a field and is scalar since it deals with the quantity of work done. Now here, this is where we're going to look at definitely questions that come in multiple choice. Most of our terms are vectors, most of them. But we know that energy and work, even though they have vector quantities with them, right? Energy and work are all scalar quantities. Why are they scalar quantities? Because they take place in any direction possible. So similarly, we're going to see that potential is also scalar because it takes place in any direction possible. It doesn't say, you know, you have to work with your PD from point A to B, and then you have to go to C, right? It's just going to move straight across. It does not just move in straight lines. So the symbol for potential is Z. Why is it Z? It's supposed to be V. My apologies, y'all. And the unit is joules per coulomb or volts. Please note the unit for potential difference is either the volt or joules per coulomb. You all have to use them interchangeably depending on your circumstance. When describing a field, potential is usually more useful than field strength. Being scalar, we can look at its effects in many directions as opposed to a unidirectional vector. So we don't really look at electrical field strength so much because it doesn't tell us much. Just as you saw here in the diagram, within the sphere, you had no electrical field. But that doesn't mean that there was no charge. That doesn't mean that there was no energy. That doesn't mean that you can move an electron from one point to the next. No. Voltage or potential difference tells us how much energy we do have to work with. So this is why, one is a little more useful than the next. Not saying one is useless. All right, just one is a little more useful than the other. Moving on. Okay, now this year is going to take some calculus, math students. You all can follow those of you all who have the AdMaths background. You can go through it and follow it. It's very simple integration. Everybody else, we're just going to jump from one point to the next. We're going to bypass the entire proof. So we want potential due to a point charge. So if we were to take the potential from moving a charge from one point to another, we can use the basic equation of work is equal to force by distance. Basic equation. We're looking at, Form 4 mechanics. And your force, that's why I have writing people here. Force is equal to, work is equal to force by distance. And when we change our work, all we're going to do to get a change in work, which is delta, delta means a change. We are not going to change the force because let's look at the force here as being the force exerted by a charge. This will not change. The amount of force exerted by a charge is not going to change. What's going to change is the distance that force is or that charge is from another charge. But the individual force that a particular charge has cannot change because we cannot change the nature of that charge. Remember, force is equal to Q1, Q2 over 4 pi r squared epsilon naught. These things do not change. The only thing that can change is how far away your object, your charge is from a next. So we cannot necessarily change the force exerted by a charge. You all that make sense? I think my class fell asleep.
Kinda.
Kinda. Read it through again. All right, let's go through that again. When we're looking at potential, remember potential tells us how much energy your charge has. We're going to look at how much work and energy are interchanged. We can interchange them. Okay, so we're going to look at how much work a charge can undergo or can carry. And we're going to have our equation of work is equal to force by distance. To get my change in work, and remember change in work will be your potential difference, right? Potential difference is your energy change. Remember we did this a while ago. Current was a measure of electrons, potential difference was a measure of energy. So potential difference here tells us how much energy it takes to move in one charge to another point. So your change in work, delta W, will be the force exerted by your charge that remains constant because my positive charge, if I take this positive charge here and I carry it all across to somewhere else, it is still going to exert the same amount of force because that charge did not change. So the force exerted by a charge will not change. What will change is how far you move that charge. So if I take a charge here, and this is my electron here, and I bring my charge closer, wouldn't there be a different amount of energy related between the two? If I have my proton very far away, not my proton, my positive charge very far away from my negative charge, the amount of energy between them is going to be small. But if I bring it very close, I'm going to get a larger energy or a larger potential difference between them because my distances between them is small. So here you're going to look at change in work is equal to force by your change in difference. But here, our distance, we don't really look at distance, we look at R, because our point charges can exert work or electrical field or attractive force in a sphere. And the only way we measure distances in a sphere is using your radius. So we're going to replace our change in distance with change in radius. So you're going to have delta W is equal to force by delta R. Math students, you all can follow this. This is very simple. This was really easy to follow. And what we're going to have to do, we're going to end up with getting an equation to learn. So for non-math students, you all have to learn the equation. Math students, do the integration, see if it makes sense. It's a really simple integration. It's just 1 over r squared integration. So your PD is given by Q over 4 pi epsilon naught. Now this is a constant value. You all know that is a constant value. 1 over 4 pi epsilon naught was equal to 9 by 10 to the 9. All right, remember we did that last day. And your Q will be a constant value because we're looking at the potential difference in moving a charge. We're going to look at the energy it takes to move a charge from one point to another. Your charge does not change. Your electric permeability here does not change. So this is your constant that you pull out of the equation and you multiply it by 1 over A minus 1 over B, where A and B are your distances from your charge. So you have to learn this equation. Let's get the highlighter up. All right, so your potential difference just for moving a charge from point A to point B is Q over 4 pi epsilon naught by 1 over A minus 1 over B, where A and B are your distances from your charge. So here we're going to look at a variant of this equation, potential due to conducting spheres. If we consider an isolated sphere, we take the second point, which is B, as infinity. Why is it infinity? Because an isolated sphere, right, say with plus charges all around it, does not have a second point, right? It has no second point to move to. We're just going to look at what is the potential difference from your sphere to some distance away. There is no second point, there is no starting point here from A point to next, because your potential difference here will be at a maximum at your sphere. Now, if B is equal to infinity, 1 over infinity is 0. It's a mathematical specialness that we just don't go there today. So 1 over B will be 0. So your V is equal to Q over 4 pi epsilon naught into 1 over A over minus 1 over B. The B will get eliminated because 1 over infinity is 0. So you're going to get V is equal to Q over 4 pi epsilon naught A. So if I want to know what is my potential difference 10 centimeters away from a charge of 1 coulomb, all I need to do is just to plug in my values into here. All right, you're going to get 1 over 4 pi epsilon naught by 0.1. Please remember, you must use SI units. So it's really simple. All we're doing here, if I want to know what is the potential difference from the start of or the very surface of my sphere to some distance away, all you have to do is plug in your charge and divide it out by your distance. It's a very simple equation. Well, it's a simple usage of the equation. So you can see how one equation leads into the next. That's clearing up the board. Now, just to remind you all, remember we were talking that potential difference is more useful than your electric field strength. Let's look at our equations again. Potential difference, or your potential just be Q is equal to 4 pi epsilon naught A over A. And your electric field strength is Q is equal to 4 pi epsilon naught over R squared. See, they actually are kind of related to each other where we have exact terms, right? We have exact terms here. The only thing difference, the A is just your different distance away from a point, and your electric field strength takes your distance in your area. So they are related. We're going to look and see how PD, which is your V, is related to your E. And I'm pretty sure you all can see already how they're excuse me, how they are related. And I just did that over. If you were to go in the mathematics of it, if you had a charged sphere, a hollow sphere, inside of the sphere with a radius of r, let's just take this diagram coming down. So we're going to take from your left and your right. This is not negative and positive. We just have a reference point from the very center of your sphere. In the middle of your sphere, your electric field strength is going to be 0. Okay, because there is no electrical field, there is no charge that exists inside of an object. And once we reach the surface, you are going to start to decrease exponential or have that exponential decay as you move away. So what it does, it goes straight up to positive and you get a graph. And we have our E is equal to 1 over 4 pi epsilon naught by Q over R squared as our first equation. Second one here, look at voltage. The voltage here is going to be constant. Why? Because the charge on your surface is the same. So if your charge is the same, your potential difference is constant. Not 0, it's just going to be constant. So in your sphere, you have a constant PD because our charges did not change. And as you reach your surface, it's going to rapidly exponentially decay as you move away from your charge. And we're going to get V is equal to 1 over 4 pi epsilon naught by Q over R. Everything here is written already on the screen. I'm just, writing it larger. So going on. From these diagrams, we can see that there is a gradient relationship between V and E. Add maths and math students, what is the gradient of a line that is parallel to your x-axis? Add math students.
Wait, that wouldn't be 0?
Would be 0. Right, very good, that is correct. The gradient of any flat line, any line that is parallel to your x-axis is 0. So here we can look at the relationship reading. As r changes, which is your x, all right, that is your x term, we can see that v is constant when e is 0. From basic calculus, we know that the differential of a constant gives 0, or the gradient of a line parallel to the x-axis is 0. So here, one point, let's just look at this. For AdMath students, you all can already see how V and E will be related to each other using calculus. Here we can see from maths, all right, the gradient of a line parallel to your x-axis is 0. And look here, for your V, we have a line parallel to the x-axis, and E, we're going to get our parallel line is going to give us 0. So that means that the gradient of your V is actually equal to E. If you were to plot a graph of all your stuff and get a relationship, put it down in very simple words. I'm not saying you're writing right now. I'm supposed to say differentiation, not gradients. But here in mathematics, we're talking about advanced level maths, you know, the foundation of physics, which is calculus. Anytime we have a line parallel to the x-axis and we find the gradient or we find the differential of that line, we will get 0. And here we can see that V is parallel to the x-axis and we have a 0 relationship. And that means that the both of them clearly are related to each other via some sort of change. So we have here, just for a non-ADMAT students, all you're going to use is E is equal to V over D. Right? Where E is the electric field strength. And here you can use D as your distance from your charge. So we have our equation E is equal to V over D. We're going to go into that actual proof. We're not going to go into that actual proof because it doesn't come again. Those of you all can give it a read. This is not, I have to check and see if it's there, but it's not in here. Our class is nearly done. So what we're gonna do, we're just gonna have here electric field strength. The electric field strength is equal to your PD over the distance from your charge. So E and V are related to each other. It's just one is divided by a distance or an R more than the next. So we're going to go through this proof next day since we do have the time to go through it next day. All right, and we're going to stop up to here. All right, and then finish up the handout. The handout is actually finished after this, but I need to take my time and go through this little proof here. We just need to take a little bit of time just to go through the proof, and then we're going to do some questions. When I have you all, not tomorrow, sometime later this week. Okay, I have you all. When do I have you all this week again?
Thursday.
Thursday afternoon. So the Thursday afternoon class might run an extra 10 minutes just, to wrap up. So we're going to do some questions on electric fields and this entire topic. So we'll do about 2-3 questions and you all will get an assignment on it so you can get the work done.